Today we are going to continue, and I hope I can finish with this chapter for the frequency analysis of linear time invariant system. So last time we are into the content of inverse system. We are looking at the inverse system, how to correct the frequency impairment from the channel or from any of those systems. And those frequency will give me frequency selectivity in the output signal that is not the same as input signal. So I want to correct that. One way to do it is using an equalizer. Equalizer is I want to equalize the signal, make sure they have evenly spread all over the frequency, flat line across all frequencies. So that is an equalizer. As for equalizer, I'm going to use the next class on a special topic of linear optimal equalizer. And that is something involved with a normal equation that we will see will be very useful. It's a very powerful tool. So I'm going to dedicate one class next Monday on that. So today, let me finish with the idea of phase, minimum phase, maximum phase, and a mixed phase system. We used an example. There are two filters, H1 and H2. It's very simple. The filter has only 1, 0, and it's an FIR filter. We have only the numerator without denominator. We just have zeros. There's no poles. Well, if you really want to talk about poles, indeed we have one pole for each one, and the pole is deformed onto the origin. Usually we don't count that. So we said that says 1, 1, 0 there. So the first one we know that is a 0 at this 0 at -1/2. Let me call that 0, 1. The second 0 for H2 is at 2. Okay, so 1, 0 or -2. So 1, 0 is within the unit circle, and another 0 is outside unit circle. One observation is that these two zeros are reciprocal of each other, meaning that Z1 times Z2 equals 1. It's reciprocal of each other. So what we'll have is we will have those two filters. The amplitude of those two filters are the same. They are exactly the same. But the phase of those two filters, they are different. As we've seen, if you put in numbers, it looks like that. It's a arctangent, which here and here, they are different. If we put that onto a plot, this is the phase, which is also the angle. This is the angle of H1 omega. And this is the angle of H2 omega. They are different. They're different. Last time we discussed about how they show in this way. We're using an example H1 that has a 0 here, -1/2, which is Z1. And we kind of trying to plot out what is this angle or the phase actually look like. And if I have a point here, which is e to the power j omega on the unit circle, with this position omega. This omega is a phase angle here. This is omega. And then we find out actually the angle of H1 omega somehow is talking about this angle right here. This angle right here with negative form. So last time we kind of calculated this angle is the difference between this and that. And then if I am a point traveling from omega equal to 0 to omega equal to pi, so doing this is omega is traveling, and then we will see we will have an angle originally starting from 0. Then we get a number, non-zero number, which is negative, and we got the most negative part somewhere here. Once we reach the final point at here, the pi, this angle also becomes 0. So it's indeed, it looks like that. Let's go negative and doing pi. Now with the similar analysis, we can plot everything. So the angle of H1 omega indeed looks like that. And the angle of H2 omega looks like that. Because I have a 0 that is outside unit circle, which is here, -2, somewhere here, -2. That's a 0, 2. So for this filter, when I travel along the unit circle, especially when I reach the point at omega equal to pi, I'm actually looking at this angle, right? So it's spread two parts. One is ending here, one is ending here. So this angle is pi. Indeed, we got a pi here. We call the first one H1, that is a minimum phase filter. That is, we look at those two extreme points, one on the smallest frequency, which is DC, one on the maximum frequency at pi. The angle of H pi subtract the angle of H0 is 0. We call that minimum phase. If the angle of H pi at pi subtract the angle of H0 is equal to pi, we call that maximum phase. And for a real coefficient impulse response, we know that because it's symmetric, it's conjugate symmetric. So therefore, the phase will always go through the origin. That is, the angle of H0 is always 0. Now, what does that mean, real valued impulse response? Well, these two examples are real valued, right? Those are coefficients 1 and 1 over 2, 1 over 2 and 1. These are real valued. So indeed, we have those two filters with the phase plot going through origin. So this is how we kind of visualize how to plot this phase. And then in general, if I have an FIA system that has m zeros, now finite impulse response system, that means I only have numerator term, I don't have denominator term. I only have zeros, I don't have poles. Or the poles are every pole on the origin. For the filter in frequency domain, it can be written or expressed in this form, right? This is a form, it's a product of all these poles, of all these zeros, excuse me, all these zeros. So we have a constant, and this is the first zero. It's in the expression is 1 subtract 0, z1, times d to the power -1, which in frequency domain, that is e to the power -j omega. And we have, this is the expression for the second zero, and this is the expression for the nth zero. In this general format, when all zeros are inside a unit circle, and then we have a minimum phase system. Minimum phase by its definition is that the phase at frequency pi subtract the phase of the filter at the frequency 0 is 0. It's just generalized to m zeros. If they are all inside a unit circle, it's minimum phase. When all zeros are outside a unit circle, we have a maximum phase system. Outside the unit circle, then the phase of the system at the frequency pi subtract the phase of the filter at the frequency 0, they are equal to m pi, because I have m zeros. So you counting everyone is a pi. So eventually the maximum phase system, this difference here is m pi. If the FIR system with m zeros has some of its zeros inside unit circle and the remaining zeros outside unit circle, it is called a mixed phase system or non-minimum phase system. So it's a mixed, right? We cannot say it's minimum or maximum. So for a system that had m zeros, we got only one minimum phase case where all the m zeros are inside unit circle. We have only one maximum phase case where all the m zeros are outside unit circle. How many mixed system that I can have in terms of placement of zeros? Well, each zero has, the placement has two possibilities, either inside or outside. So I will have 2 to the power m different FRI systems in terms of the placement of zeros. Subtract these two. One is the minimum phase, one is maximum phase. So altogether, I have that many mixed system, different mixed system. Right? It's 2 to the power m, subtract 2. That's a lot. That's a lot. So the minimum phase and maximum phase are two unique cases. A system is called a minimum phase system if it has the minimum group delay of all the set of systems that have same magnitude response. So what does this statement say? It said that for a minimum phase system, it has the minimum group delay of all the systems that have the same magnitude response. Now, of all the systems that have the same magnitude response, how many do we have? Same magnitude response. Well, we have 2 to the power n, right? Like we said before, that this is due to how you place the zeros. If you have zeros, let's say I got a real 0 here. I have another 2 complex 0 here. Now, if I move those zeros, but I move it exactly as it's reciprocal. So 1/2 become 2 here. And a 0 here, I'm doing a reciprocal. So it flipped here. This one flipped here. If you make 0 as a reciprocal, as we discussed before, we will have the same magnitude response. So h omega is not going to change. H omega absolute value, this is not going to change. That's why you do this. You just place it with its reciprocal. How many do we have? Well, it determines on how many locations, how many positions can you place those zeros. So we said we have altogether 2 to the power n. Out of those 2 to the power of n different systems, there's only one system, minimum phase system, that gives you the minimum group delay. Now, minimum group delay. The group delay, remember the group delay. What's about group delay? The group delay, by its definition, is a delay of the signal, right? It's a delay of signal. You have signal X coming in, go through the filter, I have output Y. I want to make sure that the signal is delayed the least. I don't want to have a very large tail of signal that's delayed. I want to have those processed as quickly as possible. In other words, I want to make sure that the output signal has the energy concentrated at the very beginning. I don't want to have it has a heavy tail. Group delay is also, we're looking into the derivative of the frequency, and we will see that. So group delay here, we're still using this example, Now, if you look at those two signals, two filters, H1 and H2, which one has a better performance in terms of delay? Which one has a better performance in terms of delay? Well, we said the last time, we said H1, little h1 is this. Little h2n, we're doing the inverse Z transform from here. That is 1/2 delta n plus 1 times delta n minus 1. So if you look at that, the first filter, it looks like we have a delta here at 0. We have a half. This is a half times delta n minus 1 at time 1. The second one, so this is h1. The second one, we have a half at time 0, but we have a large component here at time 1. So in terms of delay, H2 has a heavy effect of delay. H1, most of the signal energy come at time 0. We have a delayed component, but the delayed component is relatively small. It's smaller. It's only half of that. So in this case, we said H1 has a small delay, a small group delay. Overall, it's group delay. So have a small group delay. H2 has a larger group delay. And indeed, what we have here now, H1 has a 0 that is within the unit circle. It is minimum phase. So the minimum phase will give us a small group delay. Okay. So from this example, we see the phenomenon like that. A system is called a maximum phase system if it has the maximum group delay of the set of systems that have the same magnitude response. Again, the set of system, how many do we have within the set? 2 to the power n. They have the same magnitude response. So once you define those zeros, and then you can flip that zeros according to its reciprocal. It's 1 over that 0. If you do that, the magnitude response doesn't change. So how many possibilities, well, 2 to the power m. Out of that, there's only one with all these zeros outside unit circle that give you the maximum phase system. Okay, mathematically, how can we prove that? So this is, we are looking at why these two statements are true on the previous page. Let's look at a zero, which is zero, I call it A, the A here. This zero is a complex zero. So I'm putting a polar form. We have absolute value of A times e to the power j theta A. Theta A is the phase of A. So this is a zero. This is a zero, a particular. That contributes a factor 1 over A times e to the power -1 to the transfer function hc. So this is the factor or the expression that contain the zero of A, which will be on the numerator. For FIR, we just have this. Its phase contribution, let's look at its phase contribution. The phase contribution of this factor is we are taking the phase of this factor, right? So the phase of 1 subtract A times e to the power -1. Now replace e to the power -1 as e to the power -j theta. And then we replace this A as A absolute value times e to the power j theta A. Therefore, we have this line here. And then the exponential, we're using Euler identity, break that into two parts. We have a cosine omega subtract theta A plus j sine omega subtract theta A. So we have those two parts. And this combined with 1, so we have a real part here. And here I have an imaginary part here. Then the phase of that we can express as an arctangent. So arctangent of the imaginary part over the real part, right? So that's the phase contribution of this factor in my filter. Now this factor is attributed to 1, 0, A. What is the group delay? Well, group delay is we take derivative. We take derivative and put a negative sign. So the group delay, by definition, that's a negative derivative phi A omega over d omega. Right? It's derivative of the phase, and we're taking a negative sign here. So we write it here. So the group delay is equal to that. I'm using partial because that has a function of omega, that has a function of A as well, a function of other variables as well. So we fix other variables, only take derivative as respect to omega. So here is the phase, right? The phase. And then after a few calculations, now we have already put into a numerical term, that's arctangent. And from the calculus, we can calculate all these. So I save all these steps. Eventually, we will find out this result. The result of this derivative becomes this expression here, right here. So if we examine this expression on the denominator, we have a very interesting thing here. This is the absolute value of A to the power -1. This is absolute value of A. They are a reciprocal pair, which means if you change A to its reciprocal, you don't change anything on the denominator, right? That means that if I have a 0, I place it from within the unit circle to outside unit circle, but I'm doing the reciprocal 1 over A. If you do that jump, it doesn't change this denominator because you have one of those two values. It's not changing anyways. However, if you look at the numerator, I have only one term, which is the absolute value of A. So if I have a 0 within the unit circle, that means A absolute value is less than 1. The numerator gets larger. The numerator will be larger if we place that with its reciprocal. So because this is less than 1, if you replace that with absolute value of A reciprocal to the power -1, then you will expand the numerator and it become larger. That's why indeed if you play this 0 from within the unit circle, take its reciprocal, moving it out of your unit circle, you expand the numerator and you expand the group delay. You expand this group delay. So that's a kind of mathematical proof that why when we do that without changing anything about the amplitude, without changing anything about this. So you move the zeros, it's reciprocal within the unit circle to outside unit circle, you will increase group delay. Okay. Since the derivative of a phase characteristic of a system is a measure of the time delay that the signal frequency components undergo in passing through the system. So looking back into time domain, we know that a minimum phase characteristic implies a minimum delay function, as we see in our special example, H1 and H2, right? I explained that. A maximum phase characteristic implies that the delay characteristic is also maximum. I have a relatively heavy delay tail, a lot of signal, quite a lot of signal that come through this system will be slower than the previous minimum phase, go through the minimum phase system. Because we have that, now I always want you to remember that, right? This is the spectrum. Spectrum is, we can write this as omega, h omega times h negative omega. In a z domain, it's equal to that. Hz times h z to the power -1 when z is evaluated on the unit circle. So if we replace the 0 of the system by its inverse, 1 over z sub k, the magnitude characteristic of the system does not change. So place zeros inside unit circle for minimum phase. So we always want to place the zeros inside the unit circle. For all causal and stable systems that have the same magnitude response, again, we are looking at this. The minimum phase system has its energy concentrated near the start of the impulse response. That is, it minimizes the following function, which we can think of as the delay of energy in the impulse response. So formally, that's how we define it. So if you look at impulse response, I want to make sure my tail is minimized. This is the tail. It's m is for all m in as an integer is a positive term here. So n from m to infinite. That's the tail. I'm looking at my impulse response. H for causal system is starting from 0. It can be finite impulse response. It can be infinite impulse response, and but causal is coming from here. So that's the H0, H1, H2. I want to make sure that whenever you count this tail, starting here, m equals 2, and that is the smallest, the energy of that being the smallest. In a set of equal magnitude response system, the minimum phase system has minimum energy delay. In a set of equal magnitude response system, the maximum phase system has maximum energy delay, as we already discussed that using those examples. Okay. So we can extend this to general IIR system. There's a rational system function, Hz equal to Bz over Az. It is minimum phase, same statement. It is minimum phase if all its zeros are inside in a circle. And then because I want to have a stable system, then I put all the poles inside in a circle. So the poles inside in a circle for stability, zeros inside in a circle for minimum phase, for the least delay, for the least group delay. For a stable and a causal system, the system is maximum phase if all the zeros are outside in a circle. And about this system, what about the poles? Well, the poles are still inside in a circle because I want to have a stable. I said I want to have a stable and a causal system. In practice, the system we build is a causal system, and the system we build, we want it to be stable. So in practice, we always want to put the poles inside in a circle. Then for some special purpose, you want to make it a maximum phase, then we place all the zeros outside in a circle. A stable pole zero system that is minimum phase has a stable inverse, which is also minimum phase. Why? Well, a stable system, the poles are within a circle. Minimum phase, meaning that the zeros are within the circle. Has an inverse system. Inverse system is we take 1 over hz. 1 over hz. So that becomes az over bz. This is my inverse system. Let me call it hi. So the inverse system, we know we are just exchange zeros to poles and poles to zeros. Therefore, those poles are within any circle. So inverse system that becomes zeros are also within any circle. So that's a minimum phase system. Maximum phase system and a mixed phase system result in unstable inverse system because you got those zeros also in a circle. When we generate an inverse system, those zeros become poles that will be outside in the circle. So it is unstable. Any non-minimum phase pole zero system can be expressed in this form. Right? For an arbitrary system, well, we got hz, inevitably, you will have some zeros outside in the circle. So what we can do is we can always construct like this product. We put in here is a minimum phase system. So if you have those zeros, okay, like those, for hz, if you already have zeros inside in a circle, that's fine. If inside in a circle, we do it inverse here, putting that into the inner circle. So we change that here, change that to here. Put all these zeros, 1 over z is inverse, put it inside in the circle. So these 3 zeros will generate a minimum phase system. And the minimum phase system. And then you multiply, because you did that, you need to multiply something to cancel this effect. And that is an all-pass system. All-pass system is hz, this is another h, let me just h prime over h prime c to the power -1, something like that. So you have exactly those numerator, denominator that are using different z and z to the power -1. So you kind of express this effect you're doing this inverse of zeros. So that is an all-pass filter. Now that's another use for an all-pass filter, right? All-pass filter, we mentioned before, it does not change the amplitude. So the amplitude of this all-pass filter, that is always a constant. If you normalize, that's always 1. But the all-pass filter is manipulate the phase. In this case, indeed, we manipulate the phase in order to make sure that this part is minimum phase. If hz is causal and stable, as usual, causal and stable, then we can construct a bz and the b1z times b2z, where b1z has all its roots inside in a circle, b2z has all its roots outside in a circle. Then this minimum phase, h minimum, can be expressed in this term, okay? And the all-pass filter part can be expressed in this term. And you can see if I multiply these two, b2z to the power -1, b2z to the power -1, these two canceled out. So indeed, we have a bz over az. But because I'm doing this construction, then I know all these roots, b1 roots inside in a circle, b2 roots outside in a circle. Therefore, b2 as function of z to the power -1, then I have all the roots within the inner circle. So indeed, h minimum is a minimum phase system. H all-pass is a stable all-pass maximum phase system. Maximum phase, yeah, because it's due to the features of B2. Now the group delay of the system, group delay is the phase of HZ and the phase of this, right? So phase of this is the product. When you calculate the phase, you make this H minimum plus the phase of H all pass. Phase is e to the power j phase. So when you do that, it's a plus term. And then you do the derivative, the same thing. We have a plus sign here. So that will be the group delay of the minimum phase system plus the group delay of the all pass filter. Okay. All right. So finally, let's look at a system identification. System identification is that we have input signal, we observe the output signal. I want to find the system. I want to find HZ. We already know for LTI system, we have those two expressions. For LTI system, I can express that as a convolution in the time domain. So yn equal to hn convolve with xn. I can express in this division in the frequency domain or in the z domain, hz equal to yz over xz. Now using these two, I can find hn, can find hz. The system can be identified uniquely if it is known, if it's non-causal, right? If it's non-causal, that we have only one possibility, so we can find this out. Using this is relatively easy, but hz over xz, we can calculate hz, and then from hz, if it's uniquely, it's causal, then we can uniquely determine that using the inverse Z transform to that. Alternatively, if the system is causal, we can also work that out in the time domain. If the system is causal, then Yn, the convolution can be written in this form. The k is starting from 0. K is starting from 0. Then we can find those little h's using a recursive format or iteratively. So we have h0 is y0 over x0. Then hn, when n is greater than or equal to 1, we can use the bottom line, this iterative update, to find all these hns. Okay. In practice, sometimes it is a little, we have some troubles to get hn as a deconvolution from yn and xn. Okay, first of all, excuse me. First of all, the deconvolution is somehow it's troublesome. Deconvolution is complicated, and I have to do the iteration to do that. It's much nicer to see in the frequency domain or Z domain is we just one shot using a division, calculate capital H, and then using inverse Z transform, inverse Fourier transform, find little hn. The other problem is that for those signals X and Y, these observations, they will change, right? These are the signals. Signal is changing as a function changes time. So Xn will change, Yn will change. When you calculate or to identify the system, you can only take a finite window of the signals, Hn, Yn, then you do the deconvolution, find Hn. Now, how sure can you say you find a good Hn of the system, then it can work for all the future signals? It's kind of difficult. Unless those signals, Xn and Yn, they have some statistics properties, these are fixed. For example, it can take the first order statistic, that's a mean. Let's say we have a 0 mean signal. Expected value of Xn is always 0. We can also talking about the second order statistics. We say the autocorrelation or the autocovariance of my signal is a fixed number. If I know that, and I have much better of the signal, and can we use that to find the system, So that is indeed, in practice, usually we don't really work directly on the signal itself. We are taking the statistics, we are using the cross-correlation method to identify the system. How do we do that? We know for the system, if the system is Hn, Xn comes in, the output is Yn. Previously, we have already mentioned that for the same system, if the input, instead of signal Xn itself, we are using the autocorrelation of the input signal. Now, in this case, the autocorrelation is much stable, a much stable representation of the signal, because we know if the signal itself is Ysen stationary, this autocorrelation should be a fixed value. And then this output will be a cross correlation between R between Y and X. Okay. This cross correlation is also a much stable measurement than the output signal Y. So given that, now this put into my equation, we can write also in the time domain and in the frequency domain. So in the time domain is that we got this convolution. So that is the cross correlation we express using this format, convolution of H and R, and this is the convolution here. So in a simple form, that is my autocorrelation signal go through the system. So we have that. And taking its Fourier transform, we have that this becomes S sub Yx. We give a name. We also call that a spectrum, a cross spectrum, but we know physically we don't have that. It's kind of the signal of X and Y. It's cross correlation. Then it's called that a spectrum. It's a cross spectrum. Equals to, we take a Fourier transform. This becomes the system function. And then the autocorrelation is the spectrum of the signal. Convolution becomes product. Spectrum of the signal, that is easy. Spectrum of the signal, that is X omega times X negative omega. Or it is, you can write this in this format. This is also equal to X omega times X omega conjugate. So these three are the same, so we can write it that. That's just, we only have a real value, right? It's X omega absolute value squared spectrum. Therefore, Hz can be calculated. It's in this frequency domain, it's very simple. We have a division. So we using the spectrum here, divide by, we only divide by this, the absolute value, which is the spectrum of the input signal. The spectrum of the input signal is relatively stable than the signal itself. So we are using that to find Hz. So that's a usual way we do the system identification. So I think that's a good point for me to stop here. Next Monday, we are going to see extended from the idea on this page. And indeed, in general, when we build a filter, from X to Y, we want to make a very nice filter. So again, using this picture here, we want to identify or build a very nice filter that gives me all these required properties. So we have Xn give me Yn, but Xn itself can be a long streams of signal. And in a sense, it can be random. Yn is also random. Now, how can you get a portion of X, get a portion of Y to design the optimal filter, Hn, that can work for all future X? One use case is for communication, right? For communication is that the signal at a transmitter, signal to receiver, signal transmitter transmits something that's random. You don't know that. If otherwise it's deterministic, you don't have to communicate anyways. You know that what is being said. It's random. You observe something at the output at its Y. You want to build your communication system such that in future time, you also get this transmitted signal. You can perfectly decode it into the output that can be recovered, that can be showed, that can be displayed. So we are using the same ideas as to how to build a system or how to identify the system. And we using a technique called the linear optimal filtering, or just call linear optimal filter. We find a filter, it's a linear filter, but we want to find the best filter, optimal filter. So we will see that next time.